On January 30th, 2019, a spacecraft more than 11 billion miles from Earth picked up a frequency. Not a voice, not a code, not anything resembling a transmission in the way that word usually gets used. A specific, measurable oscillation in the electromagnetic environment surrounding the spacecraft, vibrating at a precise rate that scientists could read directly off their instruments the moment the data finally arrived back on Earth, more than 18 hours after it was recorded. That frequency told researchers something no human instrument had ever been able to measure directly before: the exact density of the plasma filling the space between the stars. And in the years since that first detection, the frequency hasn't stayed the same. It has climbed, steadily, repeatedly, in a pattern that broke decades of theoretical assumptions about what the space beyond our solar system should actually look like. This is the real story of what Voyager 2 actually detected once it left our solar system behind, how a frequency from outside our system is genuinely real, measurable physics, rather than a mysterious transmission, and why the specific numbers this frequency has produced over the years since have kept surprising the scientists who've spent their careers studying it. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now because we're just getting started. To understand what this frequency actually is and why NASA takes it so seriously, you first have to understand exactly what Voyager 2 is doing out there and how genuinely rare it is for any spacecraft to be capable of measuring something like this at all. Voyager 2 launched on August 20th, 1977, on a mission originally designed to last around 4 years, visiting Jupiter and Saturn before its planned retirement. Instead, it kept flying, using a rare planetary alignment, T, that occurs roughly once every 176 years, to visit Uranus and Neptune as well, making it, to this day, the only spacecraft in human history to have ever visited both ice giants. On November 5th, 2018, more than 41 years after launch, it crossed the heliopause, the boundary marking the true edge of our solar system, where the sun's constant outward stream of charged particles, the solar wind, finally loses its battle against the pressure of true interstellar space, pressing in from the other side. That crossing made Voyager 2 only the second human-made object in history, after its twin Voyager 1, to leave the solar system entirely, and left it from that point forward in a genuinely unique position, the only functioning instrument our species has ever placed directly inside the space between star systems, still transmitting. The specific instrument responsible for detecting the frequency at the center of this story is called the plasma wave subsystem, one of a small handful of scientific instruments still operating on this nearly 50-year-old spacecraft. It doesn't work the way you might picture a radio receiver working, scanning for an external broadcast. Instead, it listens for a very specific kind of natural electromagnetic oscillation called a plasma oscillation, a phenomenon that occurs when free electrons in a plasma, an ionized gas made up of charged particles, get disturbed and begin vibrating collectively at a rate directly determined by how densely packed those electrons actually are. The more electrons packed into a given volume of space, the higher the frequency at which that plasma naturally oscillates. This isn't some obscure or speculative physics. It's a well-understood, thoroughly tested principle that plasma physicists have used to measure electron density in laboratories, in Earth's own upper atmosphere, and now, thanks to Voyager 2, in the space between the stars. To actually trigger one of these oscillations, you generally need something to disturb the plasma in the first place, and that disturbance typically comes from an electron beam generated when a shockwave moves through the surrounding medium, whether that shockwave originates from a solar eruption billions of miles away, or from some other large-scale disturbance rippling through interstellar space. When that beam interacts with the ambient plasma, it excites oscillations at a frequency tied directly and predictably to the local electron density, a relationship physicists have understood mathematically for the better part of a century. Voyager 2's instrument doesn't need to guess or estimate. It measures the frequency directly, and from that single number, researchers back on Earth can calculate the density of the plasma surrounding the spacecraft with real precision, even though that spacecraft sits more than 11 billion miles away, and its signal takes over 18 hours to arrive. It's also worth understanding just how remarkable it is that this particular instrument is still working at all. Voyager 2 carries 10 original scientific instruments, and after nearly 49 years of continuous operation, several have already been permanently shut down as the spacecraft's dwindling power. Supply forces increasingly difficult decisions about what stays on and what goes dark for good. The plasma wave instrument has remained one of the survivors, alongside the magnetometer, providing two of the last functioning senses this aging machine has left. Every measurement it takes now represents a genuinely scarce resource, one more data point pulled from an instrument that cannot be repaired, replaced or upgraded, sitting on a spacecraft running on a fraction of the electricity it takes to power a household light bulb. Shortly after Voyager 2's 2018 crossing, its plasma wave subsystem detected exactly this kind of oscillation. triggered by an electron beam generated as a shock wave moved through the surrounding interstellar medium. By January 30th, 2019, researchers had a clean measurement of that specific frequency, and using the well-established relationship between oscillation frequency and electron density, they calculated the plasma density of the space immediately surrounding the spacecraft at approximately 0.039 electrons per cubic centimeter. On its own, that number is almost meaninglessly small, but the comparison is what makes it significant. Just inside the heliopause, in the outer reaches of our own solar system's protective bubble, typical plasma density measures around 0.002 electrons per cubic centimeter. The frequency Voyager 2 detected represented a density roughly 20 times higher than what the spacecraft had been measuring just before it crossed the boundary. Unambiguous, physical. Confirmation that it had genuinely entered a fundamentally different environment. And remarkably, this reading closely matched what Voyager 1's own equivalent instrument had detected years earlier during its own 2013 crossing confirmation, giving researchers real confidence that both spacecraft were reporting consistent, reliable data about the same basic environment. It's worth pausing here to appreciate just how different this confirmation was from what happened with Voyager 1 6 years earlier, because the contrast tells you something important about why Voyager 2's frequency data carries so much scientific weight. When Voyager 1 crossed the heliopause in August 2012, its own plasma instrument had already been damaged years earlier, back in 1980, during its flyby of Saturn. That meant scientists couldn't rely on a single, clean, direct frequency measurement to confirm Voyager 1 had actually crossed into interstellar space at all. Instead, researchers had to reconstruct the moment, using indirect evidence gathered from the spacecraft's other functioning instruments, tracking a sudden spike in cosmic rays alongside a corresponding drop in particles native to our own solar system, a process that took an entire additional year of careful analysis before NASA felt confident enough to officially confirm the crossing had happened. Voyager 2's plasma wave instrument, still fully intact and functional, gave scientists something Voyager 1 never could. A clean, immediate, unambiguous frequency reading taken in real time, confirming the exact moment the spacecraft left the solar system behind, without months of indirect reconstruction required to piece the story together after the fact. Don Gurnett, the University of Iowa physicist who served as principal investigator on this exact instrument for decades, has spent years studying what these frequency measurements actually reveal about the true structure of interstellar space, and what he found genuinely surprised him. The prevailing assumption, going back decades before either Voyager spacecraft ever reached this boundary, was that once you crossed into true interstellar space, plasma density should settle into something relatively steady and uniform. That assumption turned out to be wrong. Rather than leveling off, the frequency Voyager 2's instrument detected kept climbing as the spacecraft continued its journey deeper into interstellar space, rising by nearly a factor of 2 within the first several astronomical units beyond the heliopause, then continuing to climb more gradually after that, reaching approximately 0.12 electrons per cubic centimeter by the time the spacecraft had traveled out to roughly 160 astronomical units from the Sun. Gurnett, reflecting on what this pattern revealed about the physical nature of the boundary his instrument had spent years measuring, described the underlying finding in genuinely striking terms, calling it astonishing how fluids, including plasmas, can form such a distinct, sharp boundary under these conditions, rather than the slow, gradual fade researchers had long assumed would occur. That word, astonishing, deserves a moment of its own context, because it's not the kind of language that shows up casually in the career of a physicist who spent decades building and refining precision plasma instruments for NASA missions. Gurnett's own reflection on the finding went further, noting that the historical assumption that the solar wind would simply be gradually whittled away as a spacecraft traveled further into interstellar space turned out to be simply not true. What both Voyager spacecraft actually demonstrated, independently and consistently using nothing more than the frequency of a natural plasma oscillation, was that there is a genuinely sharp, distinct boundary out there, not the gentle, gradual fade decades of prior modeling had assumed would exist. The mystery embedded in that rising frequency deepened even further in the years that followed. In June of 2020, at a distance of roughly 124 astronomical units from the Sun, Voyager 2's instrument detected a distinct, measurable jump in the frequency it was picking up, evidence of an actual pressure front or shock wave moving through the local interstellar medium, almost certainly triggered by intense activity on our own Sun years earlier, its effects finally rippling outward across the vast gulf, separating the Sun from the spacecraft's current position and physically compressing the plasma around it. That specific event gave researchers what one peer-reviewed study explicitly described as definitive evidence of a genuine radial density gradient in the very local interstellar medium. A real, structured, dynamic environment, detectable purely through the frequency of a natural oscillation, rather than the flat, uniform void older theoretical models had predicted. What makes an event like that genuinely remarkable is the sheer scale of time and distance involved in producing it. A disturbance on the surface of our own sun, some eruption or outburst that occurred years before Voyager 2 ever detected its effects. We had to travel outward through the entire solar system, cross the heliopause, and continue propagating through interstellar space for a substantial stretch of time before it ever reached the spacecraft's position, more than a decade after Voyager 2 had already left the solar system behind. That the plasma wave instrument could still detect the resulting frequency shift, faint and delayed as it was, speaks to just how sensitive this 50-year-old piece of hardware remains, and just how far the physical influence of our own sun genuinely extends into the space beyond our solar system's formal boundary. Following Voyager 1's own detection of a similar pressure pulse in 2020, at a distance of roughly 149 astronomical units from the Sun, subsequent research noted that its density measurements appeared to level off at approximately 0.147 electrons per cubic centimeter, suggesting the spacecraft may have reached a broad density peak in that particular direction of interstellar space, or possibly entered an entirely new physical regime that scientists are still working to characterize. Because Voyager 1 and Voyager 2 are traveling in different directions away from the Sun, roughly 40 degrees apart in their overall trajectories, comparing their respective frequency data gives researchers something genuinely valuable. Two independent, simultaneous readings of interstellar plasma density, taken from two different locations along the edge of our solar system, allowing scientists to begin piecing together an actual three-dimensional picture of how this environment varies depending on which direction you're looking. It's worth being direct and honest about what current science does and does not fully understand about why this frequency keeps behaving the way it does, because that honesty is exactly what makes this story credible science, rather than manufactured mystery. One leading theory proposes that interstellar magnetic field lines become increasingly compressed and strengthened as they wrap around the outer boundary of our solar system's heliosphere, and this specific frequency carries real weight for understanding something much closer to home, too. The heliopause functions as a genuine shield, deflecting a substantial portion of the most dangerous cosmic radiation, high-energy particles streaming outward from distant, long-exploded stars elsewhere in our galaxy, before that radiation can reach the inner solar system, including Earth, at full strength. If the interstellar environment pressing against that shield from the outside behaves in a more structured, denser, and more variable way than existing models assumed, particularly right at the boundary itself, powerful scientific attention, now grounded in real physical measurement, rather than purely theoretical assumption. There's an added urgency to gathering as much of this frequency data as possible right now, because the instrument responsible for it won't be capable of transmitting forever. Voyager 2 draws its electricity from 3 radioisotope thermoelectric generators, devices that convert the heat produced by slowly decaying plutonium into usable electrical current. That output declines by roughly 4 watts every single year, a permanent unrecoverable loss with no possible refueling or repair mission, and NASA's engineers have already been forced to permanently shut down several of the spacecraft's original 10 instruments, simply to keep the remaining ones powered. In March of 2025, the mission team made the difficult decision to shut down Voyager 2's low-energy charged particles experiment, an instrument that had been running almost continuously since 1977, specifically to preserve enough power to keep the plasma wave instrument and magnetometer operating a little longer. Engineers are also currently testing an experimental procedure, informally nicknamed the Big Bang, that restructures how power flows through the spacecraft's remaining systems in hopes of squeezing out a few additional years of operation. Every frequency reading Voyager 2 sends home from this point forward is a genuinely finite resource, gathered on borrowed time, from hardware that cannot be replaced once it finally goes silent. Researchers currently project that Voyager 2's remaining instruments will lose enough power to function at all, sometime in the early 2030s. After that point, the plasma wave instrument responsible for every frequency measurement described in this story will fall permanently silent, and the unique, continuous window it has provided into the density and structure of interstellar space, the only such window humanity has ever had, will close for good. No replacement mission currently exists that could pick up where Voyager 2 leaves off. If a new spacecraft specifically designed to study interstellar space were funded and launched today, current projections suggest it would take at least 2.5 decades just to physically reach the same boundary Voyager 2 already. Crossed back in 2018, meaning whatever this frequency still has left to tell us needs to be recorded now, while there's still a working instrument left to record it. It's worth stepping back, finally, to consider exactly why a frequency like this matters so much to the broader field of astrophysics, beyond the specific numbers involved. For the entire history of astronomy, prior to Voyager 1 and Voyager 2 actually crossing the heliopause, every single model of interstellar plasma density had been built entirely from indirect observation. Telescopes pointed outward from within our own solar system, mathematics, and careful theoretical extrapolation. Nobody had ever had an actual physical instrument sitting inside the environment itself, continuously, for years at a time, measuring the real conditions directly rather than inferring them from a distance. That's what makes this frequency genuinely different from every previous measurement of interstellar space. It isn't a calculation. It isn't a model. It's a direct physical reading, taken from inside the environment being studied by hardware built during the Ford administration, still functioning nearly 5 decades later, sending that reading home across a gap so vast that the signal itself takes over a full day to arrive. So here is where this genuinely leaves things, honestly, based entirely on published peer-reviewed research rather than exaggeration. Voyager 2, a spacecraft originally built to survive around 4 years, has spent the years since its 2018 heliopause crossing patiently measuring a real physical frequency, produced by natural plasma oscillations in the space between the stars, from a vantage point no other instrument in human history has ever occupied. What that frequency has revealed is a persistent or rising density gradient that broke the standard assumption that interstellar space should be relatively uniform, along with real physical evidence of actual pressure fronts and shock waves, rippling through that environment years after their original solar trigger. This is not a mysterious signal from beyond our understanding. It is genuine, well-understood physics, made newly measurable for the first time in human history, and the scientist who spent decades studying this exact instrument openly called the underlying pattern. Astonishing. A word chosen deliberately by a researcher whose entire career has been built on careful, measured scientific language, and with the instrument responsible for it running on borrowed time, every additional reading it manages to send home before the power finally runs out is one more piece of a picture that, once this spacecraft goes silent, humanity may not be able to complete again for decades. If this kind of story is what you come here for, one grounded in real, published research rather than invention, hit subscribe and turn on notifications, because there's a lot more of the real universe left to explore. Drop a comment telling me what you think is actually compressing that boundary out there, and share this with someone who still thinks the space between the stars is silent and empty.